Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 2. In this lecture, we'll discuss the mass spring differential equation. This topic is covered in Chapter 15 of our textbook by Surway and Jowett. Recall from our last lecture that the mass spring system will be a model for all kinds of oscillatory phenomena, like the vibrations of a guitar string or the oscillations of a skyscraper in an earthquake can all be modeled in the same manner as the motion of a mass spring system. Therefore, it's very important for us to precisely understand the behavior of a mass spring system. More precisely, what we want to do is find the exact position of a mass spring system as a function of time. Once we have that, we can figure out the velocity and acceleration by simply taking derivatives. To find the position as a function of time, last time, we decided that we need to solve this differential equation here. We obtained this differential equation by combining Newton's second law of motion with Hooke's law for the force of springs. Basically, on the left side of this equation, we have mass times acceleration, and on the right side of this equation, we have Hooke's law. We need to solve this equation for x as a function of time. We suspect that when we solve this equation, we should see m, k, and also x initial and v initial. It's already pretty obvious that m and k play an important role in the solution to this differential equation. It's not so obvious where the initial conditions will come in, the initial position and the initial velocity. We'll see that a little bit later when we begin to solve this equation. Before solving the mass spring differential equation, let me give you an introduction to differential equations in general. I imagine that most of you have not taken a course on differential equations, so the idea of a differential equation might be quite new and alien to you. I strongly recommend that at some point in the near future you take a proper course on differential equations, simply because differential equations are so fundamental to physics and engineering and nearly every other scientific discipline. For now, however, we only need some basic facts about differential equations. You can think of a differential equation as a puzzle that you must solve. For example, I might ask you, what function do you know whose first derivative is equal to 2? So I'm thinking of a function, x of t. If you want, you can say f of x. However, in physics, t, time, is normally the independent variable, and we're interested in knowing how position depends on time. So the function that we're usually looking for is x of t. So I'm thinking of a function, x of t, and I'm giving you an important clue about this function. I'm saying that its first derivative is equal to 2. If you want, you can write down this puzzle in a mathematical form. You can say there's a function x. When you take its derivative with respect to t, you get 2. So this here is a differential equation. So this is a mathematical statement of what this word problem on top is asking you. Now you maybe need to think back to your calculus class, and perhaps you need to go through your list of functions and think about all those derivatives you took back in calculus, and hopefully you quickly realize that the answer to this question, to this puzzle, must be 2t. So x as a function of t is simply a first order polynomial, 2 times t. You can certainly verify that's the answer. If you take the derivative of 2t with respect to t, you will get 2. Now, to be really precise, you really should say that the answer is 2t plus any constant. Because if you take the derivative of any constant, you get 0. So technically, the answer to this question is 2t plus any constant. However, for now, we're going to ignore the constant. We're mostly interested in the form of this solution, not a very precise solution. Here's another conundrum or puzzle for you to solve. What function do you know whose first derivative is equal to t? So I'm thinking of a function x. When I take its derivative with respect to t, I don't get a number like 2 or 7, I get a variable t. Now think about this for a minute or two. You might want to integrate the left side and the right side, or you might want to just run through all the derivatives that you did back in your calculus class, and quickly you should recognize that the answer should be something like t squared. More precisely, the answer should be 1/2 t squared. If you take the derivative of 1/2 t squared using the power rule, you quickly see that the derivative of this function is t, so this must be the function that we were thinking of. This must be the solution to this differential equation. Here's a slightly harder problem. What function do you know whose first derivative is equal to cosine of t? To write that as a differential equation, you would say there's a function x. When we take its derivative with respect to t, we get cosine of t. Now this one is a little trickier because the answer is not a polynomial, but at this point you maybe need to run through the catalog of functions that you've learned about. You've learned about polynomials, you've learned about sines and cosines and tangents and exponential functions and logarithmic functions. And hopefully as you're going through that catalog of functions and thinking of the derivatives, you recognize that the answer to this question must be sine of t. Remember that when you take the derivative of sine of t, you get cosine of t. So we would say that this is the solution to this differential equation. Once again, you could add a constant and you would still have a legitimate solution, but for now, we don't want to get distracted by that constant. Let's look at a few more examples of differential equations. So here's yet another example. What function do you know whose first derivative is equal to x? Notice this one is a little bit trickier than the previous ones. I'm saying that there's a function x, and when I take its first derivative, what I get is the function itself. So I'm not quite telling you what I get, I'm just saying whatever the unknown function is, I get the function itself. I can write that in the form of this differential equation. There's some unknown function x, its derivative with respect to t is x itself. Now you need to once again run through the catalog of all those functions that you learned about back in your calculus class, and hopefully you remember that there was a very special function whose derivative was the function itself. This was the exponential function. In fact, this is the very special property of the exponential function. The answer to this question is simply e to the t. If you take the derivative of e to the t with respect to t, you get the function itself. Now, all the examples that I've shown you so far are first-order differential equations. They're first-order differential equations because they involve the first derivative of the unknown function. Here's an example of a second-order differential equation. What function do you know whose second derivative is equal to x? So I can write that in the form of this differential equation. dx dt with these 2's here indicates a second derivative of x with respect to t. That must equal to the function itself, x. Now, if you understood the answer to this top example, then the answer to this example should be pretty obvious. The answer, once again, is e to the t. The first derivative of e to the t is e to the t, and its second derivative is also e to the t. In fact, you can take the derivative of e to the t as many times as you want, and you will always get the function itself. So e to the t happens to be the solution to both of these differential equations. Here's probably the trickiest example that we consider today. What function do you know whose second derivative is equal to not the function itself, but the negative of the function itself? So I'm now asking you to solve this differential equation. The second derivative of x with respect to t is equal to the function times -1, let's say. So think about all of the functions that you've learned. You've learned about exponentials and logarithms and various trigonometric functions. And as you're going through these functions and thinking about their derivatives, hopefully you recognize that the answer to this differential equation should be cosine of t. Why? Well, if you take the cosine of t and you take its derivative, you'll get minus sine of t. And if you take a second derivative, you get minus cosine of t. So you get back to the original function, but a minus sign in front. Of course, you might be thinking, but wait a second, sine of t has basically the same property. If I take the first derivative of sine of t, I'll get cosine of t, and then if I take another derivative, I'll get minus sine of t, so I'll get back to the original function with a minus sign in front. So this particular differential equation that you see here actually has two possible solutions, cosine of t or sine of t. So now that we have seen some simple examples of differential equations, we're finally ready to solve the mass spring differential equation, and that is the main goal of today's lecture. The mass spring differential equation is this equation here. I've rearranged it a little bit, but now you should recognize this differential equation as a second order differential equation. There's a function x of t, and when we take its second derivative, we basically get the function itself. Actually, we get the negative of the function itself. Actually, we get the negative of the function times some constant in front. So now think about all the examples we went through and ask yourself which of the many functions that you saw has this special property, which one of the functions has this property where if you take its derivative twice, you basically get back to the function itself, but with a minus sign in front. The answer is the cosine function or the sine function. Here I will just talk about the cosine function. Everything I'm about to tell you also applies equally well to the sine function. So here what I'm asserting is that this function here is a solution to this differential equation here. If we want to know what the mass spring system is doing precisely as a function of time, what we need is this equation down here. Now notice that there's a few new parameters here. So t is simply time, you're already familiar with that, but a, omega, and phi are new. For now, just think of them as constants. We'll learn a lot more about them. Eventually, you will understand what their physical meaning is, but for now, I just want to focus on the mathematical nature of these parameters. Notice that we don't want to just say x of t is equal to cosine of t simply because we need this constant in front. We need this k over m. To better understand what omega, a, and phi are, let's take this function and differentiate it. So if I take the first derivative of x with respect to t, what I'll get is minus a sine of omega t plus phi. But remember that when you take the derivative of a cosine, you'll get minus sine, but you also have to take the derivative of the argument of everything inside the parentheses. The derivative of the argument is simply omega. We don't know what omega is. It's some undetermined constant. Eventually we'll figure out what it is, but I better write the omega out here. Now I can take a second derivative, so I can take a derivative of the sine function, and the second derivative is going to be equal to minus omega a, and the derivative of a sine is a cosine of omega t plus phi, times the derivative of the argument, which gives me another omega, so I'll write that as omega squared. Now notice that I don't yet know what omega is, but I can now figure it out. My differential equation tells me that when I take the second derivative, what I need to get is minus some constant times the function itself. Well, here's the second derivative, and I see the minus sign here, and the function itself is right here, a cosine omega t, and what I'm left with is omega squared, which must equal to k over m. So if I want this a cosine omega t plus phi to be a solution to this differential equation, it's important that omega squared be equal to k over m, or if you want, omega should equal to the square root of k over m. A little more precisely, what I'm saying is that we can take the solution, our trial and error solution, and plug it into the differential equation, and we find that minus omega squared a cosine must equal to minus k over m times the function itself, which is a cosine. Looking at both sides of this equation, you can see I have a cosine here, there's a minus sign here, there's a minus sign here, so the omega must equal to the square root of k over m, or a little more precisely, omega should equal to plus or minus the square root of k over m. By convention, we choose the positive square root. However, for future reference, note that technically the answer is plus or minus. More simply, if somebody asks you what's the square root of 4, technically you should say plus or minus 2. Either one of those answers, when squared, will give you 4. However, by convention, we choose the positive square root. Okay, so let's think for a few seconds about what we have accomplished here. We started analyzing the mass spring system. We came up with the differential equation. We solved the differential equation and we decided the answer was basically cosine. But of course, in that answer, there were some unknown constants, some parameters, a, omega, and phi, and we haven't yet determined these unknown parameters. Actually, we figured out one of them. So omega was equal to the square root of k over m, square root of the spring constant divided by the mass. But what about a and phi? We still need to figure out those two numbers if we want to claim that we have a complete and precise answer to the differential equation. So it turns out the constants a and phi depend on what the mass was doing at t equals 0. More precisely, we say that a and phi depend on the initial conditions of the problem. By the initial conditions of the problem, we mean the initial position and initial velocity of the mass. So we need two pieces of information, x initial and v initial, if we want to determine the two unknowns a and phi. Once we know these initial conditions, we can figure out a and phi, and once we know what a and phi are, we have a nice, complete, precise solution to the differential equation for the mass spring system. So let's do a practice problem now, and in solving this practice problem, you will see how those two unknown parameters a and phi are really solved for. Once again, we have a mass spring system, and we want to know what this mass spring system is doing. We want to know its position as a function of time. More precisely, find x of t for a mass spring system with m equals 2 and k equals 10. Suppose x initial is equal to 3 and v initial is equal to 0. Here I'm giving you the initial conditions. I'm telling you that this mass spring system begins its oscillations with an initial speed of 0 and initial displacement of 3 meters. Recall that we decided the solution to this problem must be something that looks like this. X of t must equal to some constant a, we don't know what it is at this point, cosine of omega t, where omega is another constant, plus phi, where phi is another constant. This is the solution to this problem. However, we need to know what a is, we need to know what omega is, we need to know what phi is. Of these three constants, the easiest one to figure out is omega. We have a nice formula for it. We know that omega is the square root of k over m. So let's start with that. Our first step is to say that omega is equal to rad k over m, k is 10, m is 2, so omega ends up being rad 5. The units here are the SI units, and it ends up being radians per second. So what we have here is a partial solution. X of t is going to be equal to some constant, we need to figure that out, cosine of rad 5t plus some other constant, which we need to figure out. The next step is going to be to take the derivative of this function here. Recall that when you take the derivative of x with respect to t, what you get is velocity. That's what velocity is. Velocity is the rate of change in position, and of course the rate of change is the derivative of that function. So the velocity of the mass spring system is the derivative of this function here. Recall that the derivative of cosine is minus sine, but of course you also need to take the derivative of the argument, so you get a rad 5 out here. I still don't know what a and phi are, but I can now figure them out using the initial conditions. Note what the initial conditions tell you. X initial is equal to 3. What that means is that x at time 0 must equal to 3 meters. But of course, I have this function x of t. I can plug in 0 in here, and what I'll get is a cosine of phi. So I have this useful equation here, a cosine of phi is equal to 3. I also know what v is as a function of t. If I plug in t equals 0, what I'll get is minus rad 5 a sine of phi, and that whole thing better equal to 0 because I'm told that the initial velocity of this mass spring system is 0. So now look at what we have accomplished. What we have in essence figured out is two equations for two unknowns. The unknowns are a and phi, and the two equations that we have are this one and this other one here. Hopefully you can solve two equations for two unknowns. It's probably easier to start by solving for phi, maybe looking at the second equation here. So if I call this equation 1 and I call this equation 2, as you look at equation 2, you should be able to quickly conclude that phi must be 0. We know that sine of 0 radians is 0, so we conclude that phi must be 0. If phi is 0, then I can plug that into the first equation, and a cosine of 0, well, cosine of 0 is just 1, and that tells me that a must be equal to 3. So the solutions are phi is equal to 0 and a is equal to 3. Of course, if you think a little bit harder about this, you realize that there is another possible pair of solutions, namely pi and minus 3. How do I know that? Well, sine of pi radians is also equal to 0. You can plug that into your calculator to verify it, although I think that's one of those things that you should have memorized by now. Now, if phi is pi, when you plug in pi radians in here, you should know that cosine of pi is minus 1, which means that a is equal to 3. So now we have solved for the two unknowns, a and phi. On an exam, you could give me either one of these solutions. On an exam, if I ask you what are a and phi, you could either give me this pair here or this pair here. A little more precisely, what I'm telling you is that this problem has two solutions. One solution is simply that x of t is equal to 3 cosine of rad 5 times t, and the other solution is that x of t is equal to minus 3 times cosine of rad 5t plus pi. Now you might be thinking, well, how is it possible to have two solutions? Well, it turns out these two functions are actually the same. If you went and plotted this function here using your graphing calculator or in a spreadsheet program, you will see that the graph of this function here is exactly equal to the graph of this function here. Recall that trigonometric functions are periodic, so you can shift them to the left and to the right by certain amounts, and you basically get the functions themselves. So on an exam, you could give me either one of these solutions, and either one would be correct. The important point here is that given the initial conditions, we can figure out the unknowns a and phi, and what we end up with is a very precise description of the position of this mass spring system. Solving for those unknown parameters can be a little bit challenging, so let's do another practice problem. Once again, we have a mass spring system. The mass is exactly like before, 2 kilograms, and the spring constant is once again 10. This time, however, the initial conditions are different. The initial position is 0 and the initial velocity is 7. So this mass spring system is not really starting its oscillations by being displaced from equilibrium. Its initial position is 0. Instead, what we're doing is we're giving the mass spring system an initial push. We're giving it a sudden kick, imparting to it an initial velocity of 7 meters per second. Once again, we want to know precisely how position depends on time. Since we've already essentially solved the differential equation, we know that the answer is going to have this particular form. A cosine omega t plus phi. So we know that as this thing oscillates, it will oscillate according to a cosine function, but there are 3 parameters, a, omega, and phi, which we need to figure out. You can call these parameters whatever you want, a, b, and c, for example, or constant 1, constant 2, or constant 3, but your textbook calls them a, omega, and phi. Of these 3 constants, the easiest one to figure out is omega, so we'll start with that one. We know that omega will equal to the square root of k over m, so plug those numbers in and you find that omega is simply rad 5. Notice that I'm using SI units here. The SI unit for angle is radians, not degrees, and the SI unit for time is seconds. So what I now have is x of t is equal to a cosine omega, which I now know exactly what it is, times t plus phi. If this is x, then v must be equal to this. So velocity is the derivative of this function. When you take the derivative of a cosine, you get minus sign with some additional constants out front. Now, according to these 2 equations, x at time 0 must be equal to a cosine of phi, so I'm plugging in 0 here, and v at time 0, at the initial time, must be equal to minus rad 5 a sine phi, so I'm plugging in t equals 0 in here, and I'm getting this function here. According to the statement of the problem, x initial, x at time 0, must be equal to 0, so I'm going to set this equal to 0, and v initial, as in v at time 0, is equal to 7, so I'll set this equation equal to 7. So once again, I have 2 equations. Here's one equation, and here is the second equation, and I also have 2 unknowns, a and phi, so I should be able to solve 2 equations for 2 unknowns. It's probably easier if you start with the top equation. In this case, equations that involve 0 are usually a little bit easier. So think about what a and phi need to be in order for this product to be equal to 0. I suppose one option is to simply say a is equal to 0, but that's not a very good option, because if we set a equal to 0, we're essentially saying that x as a function of t is equal to 0, so we're describing a mass spring system that's not doing anything. It's just simply sitting at equilibrium. We know that can't be right. So a shouldn't be 0, instead cosine of phi should be 0, and to achieve that we can say phi must be pi over 2. If phi is pi over 2 radians, then cosine of pi over 2 is 0. That satisfies this top equation. If you now take pi over 2 and plug it in here, hopefully you know that sine of pi over 2 is 1, and that allows you to solve for a. You conclude that a must be equal to minus 7 over rad 5. So the solutions are phi is equal to pi over 2, and a is equal to minus 7 over rad 5. Now, if you think about this a little more, you'll see that there is another pair of possible solutions. You could also say phi is equal to minus pi over 2, simply because cosine of minus pi over 2 is also equal to 0, and in that case, the A should be equal to positive 7 over rad 5. So the behavior of this mass spring system is described by either one of these two functions. They look a little bit different, but if you plotted them on graph paper, you would see that they are exactly the same function. Either one of these solutions on an exam would earn you full credit. And that is the end of this lecture. Thank you for your attention.